In the second part of section 6.3, we're going to look at ratios of other lengths in similar figures and the ratio of perimeters in similar figures. And the cool thing is that the ratio of any sort of length in similar figures is going to be the same as the scale factor. And remember that the scale factor is really just the ratio of the sides, corresponding sides. And this also applies to perimeters, because if you think about it, perimeter is still just a length. Perimeter is just the length around the entire outside. And that's why the ratio of the lengths is any lengths, whether it's sides or we're going to talk about perpendicular bisectors or medians or altitudes. Those lengths are still the ratio of the scale factor, or the ratio of the sides. And so is a perimeter, since that's just a length as well. And this is stated as a theorem here that the perimeters of similar polygons are in the same ratio as the corresponding sides. So ratio of perimeters equal to the ratio of the sides. You don't necessarily have to find the ratio, you don't have to necessarily find every side length in corresponding figures to be able to find perimeter. If you can find the perimeter of one of the similar figures, you can find the perimeter of the other if you know their scale factor or the ratio of their sides. And when it says ratio of corresponding sides here, I could say or the scale factor, because remember the scale factor is the same as the ratio of the corresponding sides, just simplified. Let's use that in an example here. You are constructing a children's play area that is similar in shape to a playground with length 25 meters and width 50 meters, but the play area is only 10 meters in length. Okay. I'm just going to put some rectangles here because I'm assuming it looks like we got a rectangle here. Now, if I copy and paste this and then grab that corner and make it smaller, I know these are similar. That's kind of a way I can go about that. Let's say my playground's larger, right? The playground was length 25 meters, width 15 meters. The play area is only 10 meters in length. All right. So here's my playground that had length 25 meters and width 15 meters. And then this play area, 10 meters in length. Now the length I put here, so I'm going to put the 10 meters in length here as well. Alright. First, find the scale factor of the new play area to the playground. Ooh, okay, look, I want new play area first, then the playground number second. The only number I have for play area is 10. Compare that to the new playground. The correct number, we're comparing lengths, would be 10 to 25. Reduce, divide by 5, and we get 2 to 5, dividing both those by 5. So there's my scale factor. And then find the perimeter of both. Well, I can find the perimeter of the playground, no problem. I'll do capital P for perimeter here, because I know all the side lengths. I have 2 lengths of 25 plus 2 lengths of 15. So really 50 plus 30, it looks like the perimeter of the playground is 80, Okay, 50 plus 30. The perimeter of the play area, I don't know yet. But since this is the ratio of the sides, or the scale factor, I know that that should be the same ratio as the perimeters. Now if I have play area to playground is 2 to 5, that's the same ratio as perimeter. The perimeter of the playground was 80, and that's actually the bigger number, right? So the 80 goes with the larger number, which is on bottom. I know the perimeter of the playground, but not the play area. That'll get my x. And let's cross multiply from here. I get 5x equals 8 times 2, so 160. And we should be getting 12, I believe, here. 160 divided by 5. Just kidding, 32. So x is 32. Now what is that giving me? That's actually the perimeter of this play area. Remember, because we were comparing it to the perimeter of the playground, perimeter of the play area is 32 meters. Perimeter of the playground was 80 meters, still in the ratio of 2 to 5. Now, some of you might be thinking that's not the only way we could have done this. Couldn't we have just found the width of this play area and then found the perimeter? Well, yeah. I could look at the fact that 25 to 10, or 2 to 5, is the same as the ratio of 15 to this unknown. Actually, the 15, though, was a playground, which is bigger, which would go on bottom. And the play area, we'll call this W for width. And yeah, I could cross multiply here and get 5W equals 2 times 15, or 30. Divide by 5, and I find the W is 6. And yeah, with the width of 6 meters, we have 2 10s, which is 20, 2 6s, which is 12, and 20 plus 12 would be 32. So there would be another way to do this. And I guess it would be the same amount of work either way. But it's cool to realize a perimeter is in the same ratio as the sides, and it'll be more helpful in the next example, as you'll see. In this example, it tells you right away that ABCDE, which is here, is similar to FGHJK. So these two figures are similar. First task, find the scale factor of FGHJK to ABCDE. So I know the correct order I should be writing these in. I want a number from this guy first, a number from here second. Actually, the only side length I know in this figure is 10. So I'm going to have to use the 10 in this ABCDE. And let me see here. This 10 corresponds to side DE. I'm going to use my similarity statement because it's kind of hard to tell. I mean, there's like maybe a rotation and a flip. No, just a rotation, I think. But it's harder to tell which side matches up with, corresponds with 10. But I know it's side DE. Actually, D and E were the last two letters here. So that must correspond to the last two letters here, JK. And then I notice that that side is 15 here, JK. So now I know that 15 corresponds to 10. I wrote these in the correct order. Simplify to get scale factor, divide by 5, and we get 3 to 2. If I divide 15 and 10 both by 5. So there's my scale factor. And I can use that to find x. We needed this one unknown side here. I can use the 15 to 10. I can use 3 to 2. They're the same ratio. Maybe I'll use the smaller numbers. 3 to 2 equals what to x, or x to what? Where does x go? Actually, x was in the smaller figure, right? So it goes with the smaller number, which was on bottom. What side corresponds to x up here? Now, x was side AE. AE were the first and last letters. So I'm looking for side FK, which is right here. And that's 18. So that goes on top. Cross multiply. 3 times x. 2 times 18 would be 36. Divide by 3. And it looks like x equals 12. And that seems reasonable. This side was a little bit longer. That looks good. Compared to that 10 to 15, 12 to 18 looks good. Still that ratio 3 to 2. And now this last one. So why was it important that perimeter is in the same ratio as the sides? If I want to find the perimeter of ABCDE, all I know is 2 sides right now. I know x is 12 and this is 10. I would have to find 3 more sides before I could find the perimeter. So it would be way more helpful if I could just use this ratio, because I know perimeter should still be in the ratio of 3 to 2. And then if I find the perimeter of this guy, which I can, I have every single number, then I can find the perimeter of this using the ratio instead of finding 3 missing sides and adding up. So I got to find the perimeter of this. I'm going to add up all of these sides, 15 and 12 and 18 and 15 and 9. And I'm getting 69, and hopefully that's right. This would be what, 30? Another 30 would be 60 plus 9. Okay, so perimeter of the big guy was 69. That perimeter we're going to put on top with the larger number of 3 in our scale factor. And then I can just put maybe P down here for perimeter of the little guy. So perimeter should still be in the ratio 3 to 2. It's just another length of sides. I can cross multiply here and figure this out. So 3p equals 69 times 2 is 138. Divide that by 3. And the perimeter of the smaller figure is 46. So way easier to find perimeter using the fact that it's the same ratio of scale factor than it would be to find all the missing sides and add up that way. Okay? Little discovery questions for you. Are congruent figures similar? Are congruent figures always similar? Do they have to be similar? And then reverse that. Are similar figures congruent? Do similar figures have to be congruent? Are they always congruent? And then what's the scale factor of congruent figures? So first question, are congruent figures similar? Remember, to be similar figures, you need all the angles congruent and the sides proportional. Well, congruent figures definitely have congruent angles. They have congruent sides, so does congruent sides mean proportional sides? Well, yeah. If they're congruent, they're definitely similar. Yes, always. Okay. Congruent figures are considered similar as well. Remember how the congruent sign has a similar symbol right in it anyway. Are similar figures congruent? Just because two figures are similar, like here, does that mean they're congruent? No. Similar figures have congruent angles, but remember the sides are proportional. The sides aren't necessarily congruent. So are similar figures congruent? No. Only sometimes. I mean, I guess every once in a while you'll have similar figures and they're actually congruent too. Probably not. And then last question, what's the scale factor of congruent figures? Remember, scale factor is a ratio of the sides. Well, if the figures are congruent, aren't the side lengths the same? So it'd be like 5 to 5, same number to same number, but doesn't that always reduce 1 to 1? Because no matter what, it's going to be the same number to the same number. So scale factor of congruent figures, always 1 to 1, because the sides are the same length. And then one more note here. Perimeters were the same ratio as the scale factor, but so are any corresponding lengths. If you look at medians, if you look at altitudes, those corresponding lengths are going to be the same as the ratio of the scale factor. So I wrote here, if two polygons are similar, the ratio of any two corresponding lengths, like their medians or their altitudes, is going to be equal to that scale factor, or the ratio of the corresponding sides. So you can use that scale factor, that corresponding side ratio, and consider it for any special lengths in those triangles or whatever it might be. And we'll consider some examples here. We're given that triangle MNP, which is here, is similar to triangle RST. Find the length of altitude NL. I know that NL is an altitude because it goes from a vertex to the opposite side at a right angle. Notice that SL is an altitude of this triangle because it goes from vertex to this side, and these would also be right angles. So now I know that if I'm looking for altitude NL, we'll call it X. I would compare NL to this altitude. These are both altitudes, so I'm comparing X to 14 for certain. And I want to set up a proportion. I want to compare two other numbers here. The only other length I have in this triangle is 18. So that should go on the same side of the fraction as the 14, so on bottom. What corresponds to 18 in this triangle? Is it 27 or 30? Just to make sure, I think it's 27, but ST, last two letters is NP. Yeah, so that would be 27. So I can use these corresponding sides, and that's the same ratio as these corresponding altitudes. Another length in there. Cross multiply and solve. So x times 18 is just 18x. I have to do 14 times 27, giving me 378, and divide by 18 on both sides. And I get 21 for x. So altitude NL is actually length of 21. Seems reasonable for the picture. Alright, we got another type of special length in these triangles. We do know the triangles are similar. Triangle JKL, similar to triangle EFG. Find the length of median KM. KM is here, and it is a median because it goes from a vertex to the midpoint of this side. I know it's a midpoint because of those two congruent tick marks. I know that this is a median as well because it goes from a vertex to the midpoint of this side. I know it's a midpoint because I see two congruent tick marks there. So if I want to find the length of this median, I know that I'm going to compare x to the other median of this guy, which is 35. Comparing medians here. So then I have to compare two other corresponding lengths in these triangles. And actually it's kind of cool because even these lengths aren't really sides. 48 is half of this side. 40 is half of this side. But notice these are both the sides that the midpoint is on. So they are corresponding lengths. X is in the same triangle as 48. Those are both going on top. 40 is in the same triangles as 35. Those are going on bottom. And yeah, 40 and 40 are corresponding lengths. They're both half of that side that the median is going to. So I can cross multiply and solve for my unknown median. And get 40x equals 35 times 48 is 1680. And I divide by 40 and it looks like I'm getting 42 for x. And remember that was actually median KM. So length of KM is 42. And that looks like a reasonable number. This was slightly less than the half of the side. Here, slightly less than half of the side. It looks good. So looking at the fact today that special lengths in figures and perimeters are in the same ratio as that scale factor or the ratio of the corresponding sides in similar figures.